Yes, Suresh ji. Hello.
Yes, sir.
I'm audible and PPT is visible.
You are audible, sir. Yeah, and PPT also now visible.
Okay, so let me know when to start because I'm having PPT in front of me.
Yes,
Okay.
sir. We will
You are
wait
alone
for.
there now, na?
Yeah, yeah, yes, sir. Couple of minutes we will wait because
Yeah,
the
yeah.
participant is
Okay,
yet
okay.
to join.
Okay, no issue, no issue. वीडियो नहीं मैं ऑन कर वीडियो नहीं लाऊं. Yes, Suresh ji. Anyone joined?
No,
Uh,
sir. I am alone. But
okay,
I
okay.
think they will join if you wish. We can continue, sir. Or we will wait for 5 minutes. Whatever you.
Convenient, fine.
Yeah.
Okay. I think we'll decide to start at 2:10.
Okay, sir. Yeah, yeah. We will start in 5 minutes. Maybe a
Yes,
participant is taking the lunch, sir. Maybe
whatever.
they
Yes.
will get 5 minutes late. Okay.
या आवाज येईल बरं का? आवाज येईल. आवाज येईल. हां, तिकडे बस मग. असं काही नाही, बस तू फक्त. Yes, Mr. Suresh, we will now start. Hello.
Yes, sir. We can start. I think meanwhile the participant will join.
Right, right, right. We will
Yes,
start.
sir.
Uh, so today we are going to cover this topic furnaces in paper 2. Till this moment, we have completed boilers and rather fuels and combustion, boiler and steam systems. These three topics we have covered. Now today we are reaching to topic 4 of paper 2, furnaces. Basically, I have made it clear in my previous lectures that boiler and furnace are that way quite identical, except the fluid water is not used and no question of steam formation and all. But you can get very high temperatures. If you take the example of steel industry, they all use electrical arc furnace called as EAF. EAF is widely used in steel industry arc furnaces. So all such furnaces can generate even a temperature of more than 1500 degree. You all might remember that steel melts at around 1539 degrees centigrade. What is it is called as ACM temperature of steel melting for as related to uh, production metallurgy or metallurgical engineering or whatever material science and all. If you remember iron carbon equilibrium diagram for melting of steel, you will definitely get back that steel has to be heated to 1539 degrees centigrade for getting it melted, and again for reshaping it. Scrap melting also needs this type of temperature. So all such huge temperatures can be achieved in furnaces. Only the question related to water handling, then steam, and all these things do not come into picture. So no pressure, nothing. Only the various fans and blowers do need pressure as per their basic requirement as a whole. But process does not demand any pressure. Process only needs heat, and that is called as, and such a device where only heating is achieved is called as furnace. So now there are many types of furnaces. So what are those types? First, I have preferred to go for mode of heat transfer. So open fireplace furnace and heating through the medium. What do you mean by through the medium? It means indirect heating. So directly the metal to be melted does not get in contact with the huge heat of the melting temperature. The contact with heat is in indirect way. Okay, that metal itself does not get heated to that red heat, but indirectly it is supplied with that heat, and flame does not touch the metal indirectly. So that is called as heating through medium. And when open fire takes place, the direct uh, whatever we come across in LPG combustion at home and all that, that is open fireplace furnace. So ultimately, these are the again types related to mode of heat transfer. Then if it is a batch type furnace, then it is a forging type. Batch means batch has got certain cycle time of 12 hours, 8 hours like that. So that is forging furnace. Then continuous pusher furnace or re-rolling furnace, particularly used in steel mills, rolling mills, hot rolling or cold rolling and all. Those are all batch type furnaces, and even pot type furnace in many cases is also a batch type furnace. Then there are continuous furnaces where the furnace keeps on running till the next shutdown occurs. And it is normally the example you can get quote is glass tank. So glass melting furnace or regenerative type of furnace is a continuous furnace. Then the last topic which we must know is recuperation and regeneration. So recuperative furnace is a furnace where the uh, waste heat of furnace at around say 700 degrees centigrade or 800 degrees centigrade depending on the process is recovered, and air preheating is done inside the furnace. It is called as recuperator. In case of boilers, we call this as air preheater. In case of furnace, we call it as recuperative furnaces. And regenerative furnaces are the furnaces in which same heat is used again and again, or same metal is used again and again, and it is regenerated. The process is regenerated and recycled. So ultimately, it is a regenerative type of furnace where the uh, working fluid is not replaced and same fluid keeps on heating in cycles. So it is a regenerative type. So these are all various types of furnaces, and again the performance of furnaces basically depends on the uh, drive source or the feed material, that is feeding gas or feeding fuel. So ultimately, if it is a electrical furnace, it tries to give maximum efficiency. That is, whatever heat is input or whatever heat is given to the system, the around 90 to 95% of the heat is used strictly for the process in electrical heating. So efficiency of electrical furnaces is quite high, but there are many limitations again. Most important limitation is electricity is very costly source, being a derived source. The word is very specific. It is a derived source. You get indirect energy. It starts from coal, then it ends up into electricity and so on. Okay, so that is what is regenerative furnace. Now, sorry, that is what is melting furnace. And now all such driving source like electricity in some cases is also replaced by say furnace oil, or you can say petroleum oil and all that. Okay, it can be LDO, it can be FO. then it can be even coal also. Okay. So ultimately, the driving source is many times considered to be replaced for getting economy and for getting efficiency. Okay. So I have initially put up a case study for your reference. Suresh, many people have joined now. Two, three people have joined now.
No,
Na?
no, already, sir, 5% has joined. So the total
Very
six.
nice. Very nice. Very nice. Because I'm starting a case study, so everyone should be able to join it.
Right, sir.
Okay, so this is a case study for furnace, and this is probably a problem, numerical problem asked for around say 10 or 20 marks. I don't exactly remember, but mostly 10 marks. And it is a very good question. I liked it, so I tempted it to put it in my PPT. So try to understand this particular philosophy of a furnace, where the electrical furnace is being decided to replace with a fuel fire furnace or furnace oil fire furnace. The matter is that way simple. Electrical furnace consumes 50 kWh per batch. For our simple understanding, we can see that 50 units per batch. So 50 kWh units are consumed in a single batch, and that furnace is to be converted into furnace oil fired furnace. So we have to estimate the annual saving when it is replaced with furnace oil, considering the following. So we have to consider the cost of FO, we have to consider the cost of electricity, we have to consider the efficiency in both the cases, and all such data is given here. So if it is electrical operated furnace, the efficiency is 75%. Now you decide to go for FO fire furnace, now the efficiency is 52%. Despite of reduction, huge reduction in FO fire furnace, as far as efficiency is concerned, you will find that FO fire furnace is again most cheaper. That is what we will learn through this problem. Now the number of batches processed in a year are 5,000. So ultimately, in 1 year, around 5,000 into 50, this much kWh are consumed. So 5,000 into 50 will give you 250,000 kWh in a year are consumed for this furnace, electrically operated furnace. Whereas the cost of electricity mentioned here is rupees 4 per kWh. Now, for your exam, if they are decide to ask this question, they will not change all the any of the figure in the problem, but they will change the cost of electricity to rupees 12 per kWh, because it is a present cost of electricity. And same thing applicable to cost of furnace oil. Here they have mentioned rupees 20, but they will mention now rupees 40, because nowadays furnace oil is available at the rate of rupees 40 per kg. But rest of the things probably will never change, I am very sure. So net calorific value of furnace oil is 9650 kilocalorie per kg. So based on this data, we have to see how much saving can be achieved in a year if electrical furnace is replaced by FO fired furnace. Is it clear to you all? This problem is understood, whatever is written?
Yes, sir.
Okay. So now, without going for the next slide, you can tell me how much charges are required in a year for electricity.
Around 10 lakhs is required, sir.
Very good, very nice. So 10 lakhs rupees are required for electrical furnace, where the input is electrical energy, but output is in terms of heat. So ultimately, they have mentioned 75% of the efficiency of electrical furnace. So ultimately, 50 into 5,000 into 0.75 will be the available heat for the electrical heating, and that has to be converted into kilocalorie. So 1 unit is equal to dash kilocalorie. 1 kW.
860.
Very nice, very good answers. So ultimately, you have to perform this calculation that 50 into 5,000 into 0.75 into
So why we have to put 0.75, sir?
575.
Yes, sir. Else
I have not mentioned 575.
75%, sir.
0.75, right. Because the efficiency of electrical furnace is 75%. Is it right? That is why
But
I mentioned 0.75. Because
when we are
oh,
converting into kilocalories, that should be mentioned.
and that is what, and then to be multiplied by 860. That is what I was trying to rather communicate to you. So ultimately, exact amount of heat available in this particular process throughout the year will be 50 into 5,000 into 0.75 into 860. Is that clear in electrical case? 50
Yes,
into
sir.
5,000 into 0.75 into 860. That is what is the amount of heat available. Okay, this is what
Yes,
we
sir.
will say, and this is why I was trying to convince you. So electrical heat available for melting in kilocalorie per year is 50 into 5,000 into 860 into 0.75. This is equal to 1.612 into 10 raised to 8 kilocalorie per year. This is annual heat available to the process. These all things 55,000 and all, I have written all the units. That is 50 kWh per batch, 5,000 is number of batches per year, 860 is conversion factor to kilocalorie and efficiency. So you will get 1.612 into 10 raised to 8 kilocalorie per year. This is the amount of input heat to be supplied for heating in 1 year for the desired production. Now this electrical part is as such over as far as the performance is concerned. The amount of heat input is clear to us. Okay, amount of heat available to us throughout the year considering efficiency part for the process is now clear to us. Now we go to FO part. For FO part, you will be requiring this much amount of heat for the process, but efficiency will be 52%. So FO will, we have to uh, organize FO in such a fashion that this much amount of heat is available throughout the year. Though actual heat available is 1.612, actual heat required for the process is this, we will need to supply this much heat because of the efficiency part. Is it clear till this
Yes,
step?
sir.
Yes. Thus, the amount of F4 required is nothing but this much kilocalorie divided by uh, kilocalorie supplied by 1 kg of fuel, that is 9650. That will give you amount of fuel required throughout the year. So you will need 32,124, 32,124.35 kg of fuel in a full complete year. Now this much uh, fuel and cost of electricity already we discussed, which could have been found out here also, but now we can find out cost of FO 32124 into 20 rupees per kg, which is mentioned in our problem. You can check. So ultimately furnace oil cost in 1 year is 6,42,487 rupees. So cost of FO in 1 year is this much, 32,124 into 20 rupees, which is equal to 6,42,487 rupees. 6,42,000. Here I should have written 6.42 lakh. And thus annual saving is available is 10 lakh minus 6.42 lakh, that is 3.575 lakh rupees. Is the problem clear to you conceptually? Any doubt you can ask and you can read once again.
But what about environmental effects, sir? Because of the furnace oil, it may give more environmental pollutants, sir.
That is right. That is accepted. That is your point is valid. For the sake of convenience, nowadays they may ask CNG in place of FO. Okay, that can be
Yeah.
a change
Okay.
in the that can be a change in the problem.
Oh,
But initially, people were not so particular about all this, so they were asking FO, and FO is the cheapest petroleum fuel available. Okay.
mm, yes, sir.
So now they will go for CNG or even agro waste briquettes. Okay. So that is possible. But as far as this problem in books is concerned, the concept is clear to you or not.
Yes, sir. Yes, sir. Clear.
Yes, sir. Yes.
So this is how we could understand first case study. Now we will understand various types of furnaces. Actually speaking, all these oil fired furnaces, rather FO or LDO or even CNG, these are all the types of furnaces used, and there is a detailed study given to you all in the book, but they rarely ask you about the working of these furnaces. So I have not repeated all these theory topics, but you can go through the figures given in the book in detail, and you try to understand how the furnaces work. And if you don't understand anything, you are always welcome to ask me your doubts. So the types of furnaces that are used oil fired are forging furnace, re-rolling mill furnace, continuous steel reheating furnace. Okay, it can be pusher type or walking hearth type, rotary hearth type, then continuous recirculating bogie type furnace, like railway bogie you can say, walking beam type, cupola furnace, and induction furnace. You would remember that this cupola furnace is there in even in many cases in high school syllabus also for steel melting. In say science like chemistry or physics, they try to teach you that the raw iron in the form of pig iron or something can be melted in cupola furnace uh, or blast furnace. So that is a basic furnace. Then all these furnaces are also quite common. Induction furnace is electrical induction furnace. You can call it as electric arc furnace also in some case. Then I will say this forging is very common. All forging industries do use forging furnace where the metal is forged in a red hot state. Then batch type furnaces and continuous pusher type furnaces, that is where the production is done in batches and not in continuous way and all that. So these are various types of furnaces available in the market. We'll go to the modes of heat transfer. Again, for modes of heat transfer, one thing we need to be very clear that the burner flame has to be very very precise, that it should not touch anyway to these walls or to the roof of the furnace or even to the metal stock which keeps on moving to the conveyor. So let us say that above this here the steel stock is there, and here the uh, conveyor is there where the metal keeps on moving in depending on requirement. So that particular metal which is to be heated will not directly come in contact with flame. If it directly comes into contact, the because of the flame, the metal may get corroded, or metal may get damaged, or metal may get whatever metal properties may get spoiled. So the intention is that the flame of the furnace should not be in direct contact with the metal to be melted. The main ways in which heat is to be transferred to the steel in reheating furnace are shown here. Heat is transferred to the metal stock by radiation from the flame, radiation in the form of electromagnetic waves, hot combustion products, and the furnace walls and the roof. Okay, so ultimately these walls and roof become very hot because of the high temperature. Then the radiation heat keeps on passing, so ultimately the metal keeps on getting heated. Or even convection effect is there due to the moment of hot gases in the over the stock surface. So the heat transfer mode is radiation and convection, not directly conduction. At the high temperatures employed in reheating the furnaces, the dominant mode of heat transfer is wall radiation. Since the wall gets lot of heat, the wall radiation results into heating the material. Heat transfer by gas radiation is dependent on the gas composition, mainly carbon dioxide and water vapor concentration, the temperature and geometry of the furnace. All these parameters affect a lot on the effectiveness of heating. That is CO2 and water vapor compression because of the heating process, temperature, and the geometry of the furnace, which I just now explained. That the flame should not be in direct contact with the stock to be heated. Again, the metal piece which keeps on heating or which is continuously heated is also called a stock. So your concept should be clear. If they mention stock, it is nothing but metal piece which is being heated. Okay. So this is basic introduction about modes of heat transfer. Now we will discuss how to how to find out the performance of electrical furnace. And here again the things are quite simple. Efficiency is equal to theoretical heat required in kWh divided by actual electricity consumed for melting. So it is equal to HT upon HA. So theoretical heat upon actual heat. This formula is very common in a boiler topic also for percentage CO2. The formula of theoretical CO2 percent divided by actual CO2 percent. Same way here, theoretical total heat required for melting divided by actual electricity consumed for melting. So theoretical heat required for melting is equal to, again same thing, mCp delta T, which is already well known to us. So it is, m is mass of metal, Wm, or you can say weight of metal, into Cp into delta T, plus H is included. This H should have a suffix called Fg, that is latent enthalpy. So this becomes a sensible part where the heat is being transferred from one temperature to another. So this becomes a sensible part, and latent part is gets added with the help of Hfg. So if the latent heat is required for the process, then this H has to be used. And this all mCp delta T plus latent heat will divided by 3600 will give you your answer in kWh. Okay. Is it right? So heat required for melting slag H2 is equal to, now for slag the formula is slightly different, and you have to remember this. But I have seen most of the in most of the exams, heat required for melting the slag is normally not asked. But if it is asked, the formula is kWh is equal to 1.65 into Ws divided by 3.6. Ws is weight of the slag. And if you want more simple, I can give you very simple idea for this. That is, it can be weight of slag into zero point 0.5 or something. I will immediately tell you.
Sir, weight of slag means what, sir? Slag means?
I will just now tell you. Just wait.
Okay.
Yes. So slag is what? Actually, when you keep on melting the metal, the because of uneven heating or something, the some parts get broken and light surrounding the in the surrounding area of the furnace. That becomes a slag. That is uh, partly melted metal. You can say that is slag. Okay, unburned. Okay, so what could not directly get melted and what remains in the process is a slag. Okay, so that slag heat required for that melting the slag is weight of slag into 0.45 more precisely, so as to remember comparatively, or you can even remember zero point 0.5 also. That will not matter much, but remembering this formula seems to be rather difficult. So here they have given the entire terminology. Wm is the mass of metal, weight of the metal in kg. Ws is weight of the slag in kg, which could not get burnt. Cp is the specific heat of metal, kj per kg degree centigrade. T2 is the final temperature of the metal, and T1 is the initial temperature of the metal. So theoretical heat required for melting is HT is equal to H1 plus H2. H1 is heat required for actual melting metal, and H2 is the heat required for melting the slag. Slag weight of the slag must be some 10% of the this weight of the metal. Suppose if you are melting say 100 kg of steel, in that case the slag weight will be around 10 kg approximately. Now you can understand the concept of slag. So which could not get burned fully and all that, and which could not get melted. So that is how it can be 10%. And then the heat required for melting that slag approximately 10% nearby. So ultimately that H2 can be found out by weight of slag into 0.45. Okay, is it clear? Shall we go ahead?
Yes, sir.
That is why here the loss in induction furnace is expressed in different that is percents, and you can guess that electrical furnace efficiency it's somewhere around 70%. And where is the lost heat 30% approximately, that analysis is given here. Okay, so the electrical furnaces can be broadly classified as induction and arc furnace, such as steel. For steel, obviously arc furnace is used, that is why EAF word has come into picture. And resistance furnace is used specifically only for heating, not for melting. This is what your concept should be clear. So when you call resistance heating, it is just to provide the heat for up to given temperature. But if at all you want to melt, or you want to provide the heat till the entire metal gets melted, in that case you have to use induction or arc furnace, right? Induction or arc furnace. So for steel melting, arc furnace is used. Now the losses in induction furnace, the theoretical energy required to melt 1 ton of steel is around 400 kWh per ton. If you somehow visit to the steel plants nowadays, every steel plants declares normally the amount of electrical energy required per ton of their scrap melting. Many cases I have read 420 kWh per ton or 430 kWh per ton. In some cases around 390 kWh per ton and all that. So this is how the theoretical energy required to melt 1 ton of steel is in this range. And this consumption indicates the specific energy consumption of melting steel, and many steel industries are trying to achieve these norms and to stay near or close to 385 kWh per ton. Many industries have got 420 or 430, then we can say that there is a potential to drop this electrical consumption to this level. That is what is this level is, that is why this level is called as benchmark energy consumption for melting of steel. However, in actual practice, the specific energy consumption is remarkably higher to this range, 550 to up to 950 kilowatt hour per ton. Nowadays, many industries have reached to a level of around 450 also. Okay, by using various measures of saving energy, or by applying the recommendations given by certified energy auditors and so on. So where is the rest of the energy? Power lost in the generator or panel is 2 to 4%. Power lost in capacitor bank is 1 to 3%. Power loss in crucible is 18 to 25%. Water cooled cables, bus bar and changeover switches. Then radiation loss is of the range of 7 to 9%. So major loss in this induction furnace while heating occurs in the crucible where the metal is heated. So this loss is around 18 to 25%. So the efficiency of electrical furnace is in the range of 60 to 70% because of all these losses, which can be shown even on the Sankey diagram, which we have learned in the previous topic. Do any one of you know what is Sankey diagram? Any idea about Sankey diagram?
Yes, sir. Yes, sir. We have.
Very good. Again, we may come across Sankey diagram for furnaces in next PPT. Okay. Now, performance evaluation of fuel fired furnaces. Why the efficiency is lower in fuel fired furnaces like FO, and why the efficiency of electrical furnaces is of the range of 70%, but for FO, LDO, the efficiency is around 50% or even less. What are those reasons? The stack temperature is quite high, up to 700 or 800 degrees centigrade, and air levels are excess. That is, we all know that excess O2 is used for combustion, which we have learned in boiler also. Then capacity utilization is low, or suppose if the furnace is capable of melting 1000 kg, but because of many restrictions from many customers or clients, you could put only 700 kg or 500 kg. So ultimately capacity utilization is up to 70% or 50% in that case, and this low capacity utilization results into low furnace efficiency. High stack temperature also obviously results in low furnace efficiency, because that temperature of stack gases can be used effectively for preheating the air if you just add one heat exchanger, where the heat transfer will take place between the air and the flue gases going to waste. Then radiation losses due to openings are very serious issue. Then surface heat loss is also very serious. Surface heat loss is due to mostly because of poor insulation and all that, and that batch operation involving heating, cooling, and soaking cycles. Okay, so because of the batch operation, the huge problem of thermal stresses occur. That is, let us consider one day of 24 hours, and cycle time for the given furnace is say 8 hours. Once those 8 hours are over, then you have to wait till the next batch is received for the furnace melting. So ultimately that wait time can be 8 hours, 10 hours, like that, and that will reduce the efficiency of the furnace because of the batch operation, because the furnace when gets cooled at high temperature, then sudden thermal stresses occur in the furnace, because it reaches from say melting temperature of 1500 degree to atmospheric temperature all of a sudden. So due to such a huge delta T, the and also due to such a huge delta T, there is a thermal stress in the furnace, and that results into lower efficiency. That is why, in order to get good efficiency of the furnaces, it is better to use the furnaces at full load capacity. And second thing, it should be used uh, continuously for all 24 hours without any break. Otherwise, thermal stresses will be formed. Okay. Now this is Sankey diagram which I was trying to explain in the previous slide. Uh, I have just now informed you about various losses in the furnace, which are again here listed down and shown in this diagram. And this is the Sankey diagram, where the gross fuel input given by fuel along mass of fuel and calorific value, it's shown over here. Then this gross fuel input gets reduced to net fuel input because of say moisture content, and so ultimately this may be a moisture content also. So your net fuel input is this much, and that net fuel input results into this much available heat. It is again further reduced, and that available heat goes to useful output. Then where is the rest of the energy? See, it is an accounting of furnaces. So where is the rest of the heat goes? The heat goes, rest of the heat goes majorly to the flue gases. We have all have come across this in boiler also. Lot of heat is taken away by the dry flue gases, and that is nothing but flue losses. So ultimately, in every problem of furnace analysis or boiler analysis, we have to find out the percentage loss to the percentage of heat loss to the flue gases. So this is a major heat loss going to flue gases. Another heat losses are the losses in the walls. That is, this wall becomes heated, and you find it very hot when you walk across this area because of the wall losses. Opening losses is also very well known to you, because while loading and unloading there is a gap in the furnace, and that gap directly exposes the 1500 degree centigrade melting temperature to just atmospheric pressure of say 30 degree. Because of this huge loss occurs, and that is called the opening loss. Then cooling water loss, because all these components inside the furnace are cooled by circulating cool water, so that the uh, basic parent metals used are in and around the furnace do not get damaged immediately, because you are using very huge temperature. So ultimately that huge heat has to be cooled by using the cooling water circulation. That water will slightly become hot, and then that hot water will be recycled through the cooling towers and all. So this is wall loss, opening loss, cooling water loss, and this is the stored heat which goes to the process, and these are all the losses in the furnace. Okay, any doubt?
Sir, sorry, sir. Gross fuel input, net fuel input.
Actually, gross fuel input is the net input. Gross fuel input includes the GCV of the furnace oil and all, and there is a difference between GCV and NCV. That is
Okay,
when
I am. That understood,
you,
sir. That
yes,
understood.
this net
That is
fuel
useful.
input does not consider moisture content in the entire fuel. Okay,
Okay, so the net fuel
the,
input is NCV.
yeah,
Okay.
this is about GCV and NCV. Correct.
Yes, sir.
So should we go to the next slide?
Yes, sir. Yes.
Now here I have again gone rather tried to share case study number two. In furnace, I have taken more than 6 case studies, so that your numericals concept should become more and more clear, and you should become fond of solving the problems in thermal paper, and that will help you a lot to get success in the thermal paper. So that is why I have taken more and more case studies, and I not prefer the explanation of furnaces and all that. So now look at this problem. Following are the operating parameters of re-rolling mill furnace. Weight of the input material is 10 ton per hour. You can call it as 10,000 kg per hour, or exactly 10,000 kg per hour in correct words. Furnace oil consumption is 6,000 liter per hour. Then again, 600 liters is given in liters. So ultimately, you have to convert it in kg. So ultimately, specific gravity comes into picture, which is given to us. Specific gravity of oil as 0.92. So now you can understand that the furnace oil consumption in kg per hour can be easily worked out if you multiply 600 by 0.92, so that you will get weight of the material to be heated in kg, rather weight of the fuel to be heated in kg. So furnace oil consumption in kg is 600 into 0.92. Okay, then final material temperature 1200, initial temperature 40 degree, flue gas temperature 650 degree centigrade. In if you remember in boiler topic, I always kept you on telling that the flue gas temperature should be as close as possible to 100 degree, or should be around 110 degree and all that. But here I am straightway saying that the outlet flue gas temperature is 650 degree centigrade. It is really a waste. So ultimately, air preheaters or recuperators are must in furnaces so as to recover this heat to the maximum possible extent. And that is what is the energy efficiency and that is what is the energy conservation we are going to study in this entire exam. So specific heat of the material is this is 0.12 kilocalorie per kg per degree centigrade. GCV of oil is 10,000 kilocalorie per kg and percentage yield is 92%. So ultimately yield is related to the material being used. That is 10,000 has got output yield equal to 10,000 into 0.92. Now considering specific gravity as 0.92, you can take heat input is equal to 600 liter per hour into 0.92, which gives you kg per hour, and then heat input is equal to mass into calorific value, mass of fuel into GCV. GCV given to us is 10,000 kilocalorie per kg. So ultimately heat input is nothing but 600 into 0.92 into 10,000, which is equal to 55 lakh 20,000 kilocalorie per hour. So this is about heat input. Then heat output is nothing but uh, mCp delta T, where m is again stock, that is 10,000 kg per hour, 10 ton per hour or 10,000 kg per hour. Then Cp is 0.12 kilocalorie per kg per degree centigrade, and delta T is already 1200 minus 40, which we just now came across while reading the problem. So ultimately output heat that has to be made available is 10,000 into 0.12 into 1160, which is equal to 13 lakh 92,000 kilocalorie per hour. And so ultimately 13 lakh divided by 55,000, 55 lakh, 13 lakh divided by 55 lakh will give you the efficiency of the furnace, which is equal to 25.2%. Is it clear? Now furnace efficiency is 25% means 75% heat is lost, which is lost to the flue gases, wall, opening losses, and then this cooling water loss and so on. Okay?
This percentage yield means what, sir? Percentage yield.
Yes,
92%.
you are right.
Percentage yield, sir.
Now percentage yield you are talking of is a part B of the problem. This is part A. Okay? So this is just furnace efficiency. We will talk about percentage yield in the part B. So furnace efficiency is simply clear to you or not?
Yes, sir. Clear.
Okay. Now we talk of specific fuel consumption on finished product basis. So weight of finished products is nothing but 10 ton per hour, and 92% is the percentage yield. So ultimately at the end of the process, though your input is 10 ton, at the end of the process you get melted metal in terms of 9.2 ton per hour. So rest of the 800 kg is nothing but slag, for your information, which we studied in the previous slide. So slag has got formed in the balance 8%, right?
Yeah.
Now furnace oil consumption is 600 liter per hour, and this liter has to be converted uh, in specific fuel consumption, because 600 liters of oil is required for melting 9.2 ton of effective output material. So 1 ton needs 65.2 liter of furnace oil or FO. Okay, this is how specific fuel consumption on finished product basis can be worked out. Try to understand the meaning of each term involved. Finished product is 9.2 ton per hour, which is considered over here. And specific fuel consumption is nothing but 600 liters per hour. And we wanted answer in liter per ton. Okay.
Uh,
Shall we go to the next slide now?
yes, sir. Yes.
Okay. Now this is one more practical slide which I try specifically decided to introduce. Measuring instrument for furnace performance. Which are all the various instruments used when you work for furnace efficiency measurement? What are the performance measurement criteria? So we'll try to understand all these one by one. uh, furnace instrumentation. So ultimately, what are the parameters to be measured? Are furnace soaking zone temperature, then these are all the parameters measured, and they are measured at these locations. These are the instruments that are required, and the expected values are in this range. So what are the major parameters measured when the furnace performance is to be measured? This is how the problem statement gets formed with the help of this particular slide. So now you want to know the furnace temperature of reheating furnace during soaking or during other operations. So ultimately, if you want to measure at soaking zone, the location of measurement is soaking zone side wall. If you want to measure it at some other location like input side or exit side, then that side temperature has to be taken at that particular location. Now the instruments required are platinum or platinum rhodium thermocouple with indicator and recorder. It will indicate the temperature at required location, and it will be even recorded also. So that is how the thermocouple or dissimilar metals combination like platinum and rhodium is used for measuring the soaking zone temperature, and soaking zone temperature is in the range of 1200 to 1300 degrees centigrade. This is how furnace soaking zone temperature has to be measured. Then flue gas is obviously the gas going out of the system because of the air and unburnt fuel. So flue gas temperature is calculated or is measured at the flue gas exit from furnace and entry to the recuperator. When it enters to the recuperator, I already told you that recuperator itself is a waste heat recovery device for preheating the suction air for the furnace. Okay, so it is measured at flue gas exit or recuperator after the or the recuperator entry. Flue gas exit or recuperator entry. Here you can take the measurement for flue gas, and the instrument used are again alloy steels, chromal aluminium or thermocouple with chromal aluminum thermocouple with indicator. So this is what is the instrument used for the flue gas measurement, and the required value is maximum 700 degrees centigrade. Okay, next is flue gas. It is used, location is measured after the recuperator. That is a flue gas temperature which which really goes out of the system to the environment can be or should be measured after recuperator. That is most correct, and it is measured with the help of mercury in steel thermometer, and the flue gas which goes to waste after preheating of air or something is 300 degrees centigrade. So rest of the 400-degree temperature is used for preheating of the air. Now furnace earth pressure in the heating zone. So near charging inside and wall over the hearth level. So instrument required is low pressure ring gauge, and low pressure gauge ring gauge means gauge which can measure the pressure in say least count of 0.1, that is 2.1, 2.2, and so on. So the furnace hearth pressure in the heating zone, and that is why the required value is between is plus 0.1 mm of water gauge. Here actually they are measure the pressure in mm of water gauge. So this furnace hearth pressure is measured near charging inside wall over the hearth level. So this is how the parameters, location of measurement, and the instrument required are tabulated. Next is flue gas analysis, which has to be done near charging inside wall, where the flue gas goes away to the environment. So it is the instrument required is actually flue gas analyzer or fuel efficiency monitor for oxygen and temperature. Required value is O2% is equal to 5. Already I told you that oxygen percent for best combustion should be around 3 to 5%. Same thing is mentioned over here. The temperature of the furnace at exit is around 700 degrees centigrade. So this is flue gas analysis. Then billet temperature has to be measured at any portable location wherever the billet is in front of you, and you can directly use infrared or laser pyrometer or optical pyrometer, and required value of the billet temperature can be is dependent on the location where you measure it. If you measure it at the entry before heating, the billet temperature will be atmospheric. But if you measure the temperature after it gets red hot, the billet temperature will be around 500 degrees centigrade or so on. So this is what is the overall judgment, and this is what is the measuring instruments used for measuring the performance, furnace performance. Okay.
Yes,
Now,
sir.
now how can you improve the performance in furnaces? How you can get the furnace efficiency say more than 25%? Recently, we could understand that the furnace efficiency was 25%, and you are really interested, or you are really interested in reducing possible losses and to improve the efficiency from 25 to say 40, 45 or like that. What are the general fuel economy measures you can take so that furnace efficiency will be improved? So first measure is complete combustion with minimum excess air. Already I told you that this O2% should be much less than 5 or around 3 to 5%. So that is the first measure they can take, complete combustion with minimum excess air. Okay. Second is uniform heat distribution or correct heat distribution. Then third is operating the furnace at desired temperature. Then reducing heat losses from the furnace openings. Maintaining current amount of furnace draught. Draught is already known to you now. Or should I explain what is draught?
Yes, think.
Draught is known, na?
Not known, sir. Not yet come, sir.
Okay, okay. Draught is very well required in furnaces. Sorry, boiler. Furnaces and boiler both. So draught means what? The difference of pressure between flue gas exit and flue gases when they are inside the chimney. A draught is created when the suddenly the flue gases go out to the atmosphere. So pressure of the flue gases while going out of the chimney, and difference that is difference in pressure when the flue gases go out of the chimney and when the flue gases are inside the chimney. So that pressure difference is called as draught. Draft. Sorry, draught. That is why the words FD fan and ID fan do come into picture. That is why we call it as ID fan is induced draft fan. FD fan is called as forced draft fan. And that draft word has come into picture because of the furnace draft. Okay.
Okay.
Now, optimum capacity utilization is very well explained. You have to utilize the capacity of the furnace to the maximum possible extent, up to 70, 80, 90%, and so on. The more the capacity utilization, more is the efficiency for your process. Okay. Wasted recovery is equally important from flue gases. Minimum refractory loss, because of the refractory condition getting deteriorated after 1 month or 2 months. Many industries I have seen in steel sector and in other metal sectors do keep on uh, organizing shutdown for their plant, and they repair the refractories. And there is no permanent solution which can directly avoid this particular thing, because the furnace uh, refractory keeps on damaging due to exposure at very very high temperature, up around say 800 to even 1500 degrees centigrade. So there is a limitation on the capacity of the refractory to withstand the
High temperature.
losses. or withstand the losses due to high temperature. So that is how the refractory has to be repaired continuously within a month or so, and to ensure that minimum refractory losses take place and minimum damage to the refractory takes place, and the damage particularly takes place because of the exposure to high temperature. And last is use of ceramic coating. Mind well, for insulation purposes and for all other purposes, particularly uh, to improve the losses due to radiation and all. Major cases where the temperature exposed is around more than 300 or 400 degrees centigrade, the ceramic coating is very important, and ceramic coating is very uh, important for rather protection against high temperature of uh, 500, 1000, 1200 degrees centigrade. So in order to get good effectiveness of insulation for high temperature furnaces, it is always preferred to go for ceramic coatings. So use of ceramic coating is very important for performance improvement. Then minimum loss of refractory is also very important. Waste heat recovery is as usual very important. Then complete combustion with minimum excess air, which already I have explained percentage to you for combustion. Then correct heat distribution. Uneven heat distribution will lead to the uh, rejection of partial batches, and all such parameters are very important for the fuel economy in furnaces. Okay, so all other losses like loss from openings and so on, loss from the walls, loss from the refractory insulation and all that, all these things, if you are able to control or save, your furnace efficiency will improve a lot. Okay.
Okay, sir.
This is why I have tried to show you this particular sketch from the book. That is, if heat is distributed in the furnace, the flame should never ever touch the wall. That is why this is wrong location of the burner flame. And if this entire wall is exposed to that high temperature, obviously your metal or stock to be heated will get damaged. So this is the correct method where there is a clear gap between the two burners and there is a flat portion available. So this is correct heat distribution, and this is most correct, I will say, because again this is a open place. Okay. And then if this flame by some means touches the stock, then the heat distribution is wrong. So these figures are self-explanatory, better for your understanding. Okay, this is the flame which keeps on touching the stock, so obviously it is wrong. But if this flame is like this, which does not directly come into contact with this particular stock, then that heat distribution is correct. Okay.
Yes, sir.
Now here I have tried to explain one waste heat recovery device, that is preheater for air for combustion in a recuperator. This is a preheater which is very simple to understand. This is particularly preheater or recuperator. This blue part is the recuperation part. These are all the burners for burning the uh, stock to the required temperature, that is fuel burners. And then here the combustion air is preheated after the circulation through the heat exchanger. And this is the electrical control panel. This is the cold air, and this air becomes hot once it touches the heat is indirectly passed over these recuperators. Then the uh, you can preheat the combustion air. Okay, and this is all the cold air flow. This is the furnace burner, and then this is the exhaust, which has to be reduced by, on percentage CO2 or percentage CO basis and so on. And this is the fan which moves the air and sends to the uh, preheater. Okay, is it clear? You
Sir,
can see
this
this figure.
combustion air fan is taking the air from exhaust, right? What you have shown.
Not
That
from
is
exhaust, not from exhaust. It is taking fresh atmospheric air.
uh,
It being air
combustion air
preheater.
fan, sir. How it works, sir? Combustion air fan.
Right. This is also called as FD fan, forced draught fan. This combustion air fan works on the principle of mechanism that the uh, furnaces get uh, forced air when the combustion actually takes place. So ultimately, amount of air used for combustion is fed in a forced manner, so that correct quantity or uh, exact quantity of air can take part in combustion with sufficient excess air. So ultimately, this combustion air fan facilitates to supply air for the combustion. Okay. Yes.
Okay, sir.
So again, here there are two types of recuperators: radiation and convection type. Okay. Now here again there is one more solved problem. Case study. I think it is fourth case study. Let us see. Two. So this is third case study. This slide is unfortunately double, and this is the correct slide. Same slide is this. I have unnecessarily gone into double. So you please read this problem and tell me how to find out the sensibility carried away by the exhaust gases. You just go through this problem. If you have any problem, you ask me, and then we'll start solving this problem. I will take 1 minute break for that. Okay. Is the problem understood to you all? See, average O2% in flue gas is 14%. So here the amount of excess air is very very high, and heat loss to flue gases is very very high. When you are using a fuel like furnace oil and all that, the flue gas O2% should be less than 5 or nearby 5. Okay. So this problem will result into very low efficiency based on the given data. The delta T is 200 to 35. It is 165 degree. The flue gas exit temperature, they have used air preheater. So the air is preheated to 300 degrees centigrade. The oil used is 440 liter per hour, and with specific gravity it is 440 into 0.92 kg per hour. Then calorific value is mentioned. Then air fuel ratio is mentioned. A specific heat of air is 0.24 kilocalorie per kg degree centigrade, and for flue gas it is 0.23. So this is a general as such data which is very common as such. Okay.
So the ratio is 14:1, sir, for
Yeah, yeah, yeah.
combustion.
What,
The
what?
ratio, the ratio of theoretical air required is 14:1, sir, generally.
That is what is mentioned over here clearly. Theoretical air required is 14 kg of air per kg of oil. So oil 1 kg and air 14 kg.
Oh, that's okay, but you are telling it should be 5:1.
No, no, no. I'm not talking of air fuel ratio. I'm talking of percent O2 in flue gas, which is 14%. This 14% O2 is very huge O2. Is it right? This
Average O2 percentage in flue gas.
right.
Sure.
That I'm talking of this O2 percent.
O2%.
It should be
Okay.
less than 5, I think.
Acha, O2%.
Right.
Understood. Understood.
Yes. So now energy input for the process is what? Mass of oil into calorific value. Mass of oil is what? They have
Mass of
mentioned
oil is
440
440.
into 0.92 into 10,200. So all this calculation will give you input energy for the process. 440 into 0.92 into 10,200. Is it right? This is calorific
Yes, sir.
value. So
Yes,
ultimately
sir.
energy input is 42 lakh 28,960 kilocalorie per hour. Whenever you use the mass into GCV or MCP delta T formula, your answer should be in lakhs. Then only it is correct. Okay, it should not be 4 digit or 3 digit like that. That will give you indication that your answer is correct or not. So ultimately it is 42 lakh 28,960 kilocalorie per hour. Now excess air, already I told you that the percentage of 2 is high. Accordingly 14 divided by 21 minus 14, that is why excess air is 200%. Okay, 14 divided by 7 is 2. So 200% excess air is used. They say that the theoretical air required is 14 kg per 1 kg of oil, but actual mass of air used is 42 kg per kg of oil. Is it right? 42 is correct or 28 is correct, or what do you think?
Which one, sir? Actual mass.
AAS, actual mass of air supplied. They say that it is 42 kg per kg of oil. Is it clear? Are you able to see the slide?
Yes, sir. Yes, sir.
So here I mentioned 42 kg per kg of oil, correct? AAS, actual mass of air supplied.
Acha,
Yes, yes,
200%.
correct, sir.
42
200%.
is correct or 22 should be there. 28, I'm sorry. 42 is correct or 28 is correct. If it is
14 plus, sir.
28, if it is 28, then it is 100% excess air.
100%. Correct.
Right. This is what I wanted to make you clear. That is why I specifically mentioned 14 into 1 plus 200 divided by 100. So 1 plus 2, that is 3 times of 14 is 42 kg per kg of air. So see, for perfect combustion you need 14 kg of air, but actually you are supplying 42 kg of air per kg of oil used. And that is how you are supplying huge excess air in this process. Okay. Now sensible heat lost in the flue gases is mCp delta T as usual, but m mass of fuel is 42 kg of air plus 1 kg of oil is flue gas weight is 43 kg per kg of oil. So m is 43. Cp for the flue gases is 0.23 mentioned by them. Delta T is 300 minus 35. Is it clear? 300 and 35 both are given to us. Oh, sorry, this is 200. Combustion air is preheated and 300, they are mentioned in the problem or not.
No, exit temperature is 300 degrees centigrade, sir.
Where it is mentioned? Oh, correct. Correct. This is what I was looking for. I'm sorry.
Exit
This
temperature
is,
after the
yeah,
preheated.
yeah. This is why we need to read the problem and understand the problem word to word. Otherwise, we get confused. Someone will say that array 200 should have been used, but 200 degree is the temperature of hot air at the outlet of air preheater. Okay, so 300 is correct. 300 minus 35, and that is how 43 into 0.23 into 265 is nothing but 2620.85 kilocalorie per kg of oil. So in all, if you are using 404.8 kg of oil per hour. Now from where I have brought this 404.8? What do you mean by this 404.80?
440 into 0.92.
Very correct. This is how you are attending to the problem. Very nice. So that is what is the correct answer, 414 to 0.92. And that is nothing but 404.8. Because you have to express this mass in kg per hour. Okay. And they have mentioned in liter per hour. So liter has to be converted to kg by this way. So that is how 404. So in 1 hour, you supply or your heat lost in the flue gases is 10,60,920 kilocalorie per hour. Now here your input energy is 42 lakh, of which 10 lakh you have lost in the discharge of through the flue gas. So 25% energy is lost in the flue gas. Approximately 25. It is even more than that, isn't it?
Yes.
So sensible heat lost in the flue gas as percentage of input energy is 25.7. Okay, and that is why in order to take the advantage of heat going out of the flue gases, they have decided to preheat the combustion air, and then that air is preheated from 35 degree up to 200 degree. So you could save say this much amount of heat out of 10 lakh kilocalorie going every hour. So this much amount of heat is saved on the basis of mcp delta t. Okay, so m is 42 kg of air per hour, 14 into 3. Cp for air is 0.24 mentioned by them. For flue gas it is 0.23. So 42 into 0.24 into delta t is 200 minus 35. This is all equal to 1663.2 kilocalorie per kg of oil. Okay, so again every hour you are losing 1663.2 per kg of oil, and you are using 404 kg of oil every hour. So you are able to utilize 6,70,000 to 3,263 kilocalorie per hour of air as a advantage, or you are able to preheat that air, and you can save this much amount of heat out of 10 lakh 60,000. So ultimately total heat used supplied is 41 lakh, and you could recover this much amount of heat. So heat gained by combustion air as percent of input energy is 16.3%. So 16% heat is recovered by installing air preheater. So whenever the flue gas temperature is very high, or whenever the excess air used is very high, in that case it is better to use air preheaters or waste heat recovery devices. Okay,
Yes, sir. Yes.
Here we are using 200 degrees centigrade, sir. Correct.
for combustion air.
Heat gain by combustion air.
Yes, and that is mentioned. See,
Yes, sir.
air is preheated from ambient temperature to from 35 to 200 degrees centigrade.
Yes, sir. Yes.
Okay,
Okay, sir.
I have three more case studies. We will go one by one. If all these three case studies are clear to you, next will be easy. If there is any doubt, you can ask me.
Okay, sir.
Now, next case study. The efficiency of a reheating furnace operating at 10 ton per hour, consuming furnace oil of 230 kg per hour for reheating the material from 40 degree to 1100 degree centigrade. Consider specific heat of the stock or material. Here material word can be replaced by stock, mind well. Stock does not mean any different word. Stock is nothing but the material for furnaces. Whatever material is fed to the furnace, it is nothing but stock, because that stock has to be processed by you. So you should not get confused. So the CP for the stock is 0.13 kilocalorie per kg degree centigrade, and calorific value of furnace oil is 10,000 kilocalorie per kg. So can you find out the efficiency of a reheating furnace? I will purposely not open the next slide, and I will expect your answer to this question. Now here the concept is very clear. Mass of stock is known to you, 10 ton per hour. CP of stock is given, delta T of stock is given. So you can find out MCP delta T as heat output required, and heat input supplied is what? Mass of fuel, which is given to you, and calorific value is also given to you. Please try to find out the efficiency. Your answer may be wrong. I will wait for 2 minutes. It is an
Yes, yes, sir.
objective question of 2 marks asked in the exam. If there is any doubt, you ask me, but I will not open the answer slide. Yes, any difficulty in solving the problem? Very simple one. No one could get answer till this moment. Please let me know if any difficulty.
Sir, mass is MCP delta T, mass is 230, sir, here.
Arey yaar, how mass is 230?
Sir.
230 is the mass of furnace oil. They have mentioned 230 kg per hour of furnace oil.
Yes, sir.
So in the first, before 230 kg per hour, they have mentioned one more thing. What is that?
10 tons per hour.
It is the mass to be processed in numerator or output.
Yes, sir. Yes.
So 10,000 is MCP delta. MCP delta T, in that M is 10,000. CP is already mentioned.
Yes, sir. Yes.
It is good that you asked me questions so that I could understand you are attempting it.
Going to 0.13 into 1060.
Very good. This is the numerator part. Output
So,
energy
13
divided
lakh
by,
78,000, sir.
that is right. Now about
13 lakh.
Okay, now go to the denominator.
Yes, sir.
Input
Denominator.
energy. Input energy is what? mass of oil into calorie DCV of oil, isn't it?
Yes, sir,
So
boss.
mass of oil is what?
230.
And GCV,
GCV is around 10,000.
right? That will give you answer to the problem.
Is it coming 59%, sir? Something?
59.91% is the correct answer. If
Yes, sir. Yes.
everyone has got it, then I will be happy.
Yes,
Every
sir.
one
Yes.
of you
59
must get it.
23 lakhs. %59.91%, sir.
Very good, very good.
Yes, it's
Every
simple,
one
sir.
of you should must get this answer. Then only the today's lecture is somehow successful. If someone is not getting, please tell me.
It's a brief one is half 10 does.
You can mutually discuss and solve this problem so that you all will understand it.
Sir, what is in the operating 10 tons per hour, sir, actually?
That is the amount of stock which is being used per hour. Furnace is in operation with the mass of stock that is being
Acha.
consumed per hour.
Oh, see, this much
That is
stock is being consumed.
that is why I will say stock. Stock means the output, the metal that has to be processed. Is it okay?
Yes, sir.
sir. Yes.
See,
Proceed.
can we go ahead or someone is not able to get the answer? Everyone is okay with 59.91%?
Yes, sir. Yes, sir.
Yes, sir. Yes. You can
Those who could not, who have got some doubts, can see this slide for a minute. Then we'll move ahead. Okay?
Mass of stock are the risk.
Okay, now we go to the case study number 5. The
Okay.
efficiency of a billet heating furnace with an output of 15 ton per hour was 32%. Okay? Now efficiency is directly mentioned in this problem. Find out the specific fuel consumption in liter per ton of billet heating and total fuel consumption per hour as per the data given below. Now again it is clear that the output mass to be operated in the furnace is 15 ton per hour, and delta T for that metal to be processed is this, that is 1100 degrees centigrade, and that billet has got specific heat equal to this. So ultimately output heat required is equal to 15,000 into this difference into 0.12. Is it clear? Now density
Yes,
of furnace oil is 0.95 kg per liter and GCV of furnace oil is 10,000 kilocalorie per kg. Okay, so this all is
sir.
related to the furnace oil, these two parameters, and the efficiency is already mentioned. So ultimately you have to find out the mass of furnace oil being used for the process, and that has to be converted into answer. If you get in liters, that has to be divided by ton of billet, that is 15. So ultimately you will find out specific fuel consumption in liter per ton and then total fuel consumption per hour. So this is how you can solve this problem. Okay?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Yes.
CP. CP is point.
You may initially find out mass of fuel in kg per hour, then that can be converted into required answers. But at least you should get mass of fuel in kg per hour.
0.32.
0.32.
Yes, sir. Efficiency, sir.
It is the efficiency. You want to find out mass of fuel required in kg per hour.
Yes, sir. Yes. 19,80,000 is the output, sir.
Right.
61,87,500 is the input.
Correct.
So then I have to calculate the mass.
Mass of fuel in kg per hour.
Mass is equal to 61,87,500 by calorific value GCV.
Right.
But we are 618.75.
Correct.
Yes.
Again, this is in kg per hour, and you want to find out in liter per ton. So ultimately, this kg has to be converted to liters.
Kg to liters is by point.
Correct. By 0.95.
0.95. So mass is equal to 618 by 0.95. 651.3.
Correct. And this 651 liters consumption is per hour. But in 1 hour, you are able to process 15 ton of furnace, 15 ton of output metal. So this 651 will be divided by 1.5, and that will give you specific fuel consumption in liter per ton. Is it
This is kg, sir. This 651.37 is
in liter? Na? You have used 0.95, then it is in liter.
in liter per hour, correct? Liters
Correct.
per hour.
Right.
Liters per hour.
Now, in this particular consumption you have found, you have processed 15 ton of metal in 1 hour. So
Yes,
this has
sir.
to be divided by 15 to get the answer in specific fuel consumption in liter per ton.
15,000 will be converted to 15.
Hmm. You need not convert. Your answer has to be divided by 15. So your answer will be in liter per ton. You want specific fuel consumption in liter per ton.
Correct.
Look at the arrow which I am trying to show. Liter per ton. Correct?
But steps are important. Write up is important, sir. We are not able to get the write ups.
Exactly. You can directly made calculation orally also. But write up is very important, which will make you understand the exact gravity of the problem.
Yes, sir. Yes.
That is why numericals are difficult according to people. In fact, I feel that numericals is the most easy part of any given engineering paper. Only you have to be very cautious.
43.4.
Correct. 43.42 liter per ton. Is it now clear to you?
Yes,
You
sir.
can
Yes.
see, you can check your answer. And then there is one more question asked by them. Total fuel consumption per hour. Have you found out fuel consumption per hour?
Mhm.
Fuel consumption per hour is already found out. 618.75 kg per hour. Isn't it?
Yes, sir. Yes.
That is already found out.
Output energy to be supplied. That is important, sir. Right. Output energy to be.
Okay. Now this problem is clear to you all.
Yes, sir. Yes.
Then we go to the this case study number 5. We have 6 cases to be solved. Now this is case study number 5. A furnace output is 5000 kg per hour of billets. Thermal efficiency is claimed to be 25%. Specific heat of billet is 0.12 kg per kilocalorie per kg degree centigrade. Billet enters the furnace at 40 degrees centigrade and leaves at 1200 degrees centigrade. Calculate the hourly consumption of in liter of furnace oil if GCV of the oil is 90 to 100 kilocalorie per liter. I think this problem is not at all difficult. If you have any
Sir,
difficulty, please ask me.
furnace output is 5,000 kilocalorie per hour. Building furnace thermal efficiency is clean. So output energy to be supplied. Output energy is equal to MCP delta T. 8,000 CP is 0.1 delta T 1200 minus 41 1160. Output energy is 66 lakhs 96,000.
Okay. But you have to find out mass of oil, na?
Oh, yes, sir. Yes. Okay,
Mass of oil in liter.
so efficiency is equal to efficiency is given to 0.25. So input energy by 0.25. Input energy is 27 lakhs 84,000. GCV is equal to 92 kilocalorie per liter. 9200 into
Check whether you are correct or not.
0.95 kilocalorie. 9200. 0.95. GCV we got it. Then mass is equal to by GCV.
Is it clear? Answer is in front of you.
Acha 287.48
Correct, correct.
5.48 kgs per hour. Simple only. Input energy required. Input energy is equal to mass into GCV. Mass of oil. Mass of oil is equal to 0.95. Mass of oil per hour is equal to output is required for billion. Input.
Is it all okay?
Yes, sir. Okay.
Sir, this 0.95, where it is given, sir, in problem? 0.95?
No, it is assumed density of furnace oil is 0.95. You
Yeah,
can
that's
assume even 0.92 also, no problem. Okay. When it is not given, you have to assume it. This is a problem actually unsolved in the book. All unsolved problems in the book I have taken as case study for your convenience, because you can solve the solved problems and you can copy from the book and you can solve the solved problems. But I have purposely taken unsolved problems so that your concept will be totally clear. Okay. So
yes,
these
sir.
are all unsolved problems, and they are expecting you to assume density of furnace oil as 0.95. Sorry, specific gravity of furnace oil equal to 0.95. And you can clearly write in such case, we have assumed this 0.95 as the specific gravity of furnace oil. You can clearly mention. Okay, and
Okay.
to
But
you
if we
and for
assume
your
around point 0.9,
huh?
if our assumption is not 0.95, suppose it is 0.94 or 9.9, then
I
answer
say
will be
every
different. No?
answer will be different, and all different answers are in the same range, and they accept all answers from 0.91 to 0.99 are correct. Okay.
Okay.
So there is a
Yes.
range of answer. There is no accurate answer in all these exams. You must have clear cut idea of the entire situation. That is what is expected. Is it okay?
Okay, sir.
Okay, sir.
Now last case study. Reheating furnace output is 10 TPH. The billets are heated from 50 degree to 1200 degree. So this is the output part, and the CP of billet is also 0.12. So output part is clear at this point itself, here itself. Now it is the input part. The oil consumption rate is 700 liters per hour. Specific gravity of FO is 0.95. Net calorific value of FO is 9650 kilocalorie per kg. Find out thermal efficiency of the furnace on NCV basis. Because you have been given NCV of furnace oil. Now here liters has to be converted to kg. That is why specific gravity is also given to us. Okay.
Yes, sir. Output heat energy.
You have got the answer to output.
Output heat energy calculated, sir. 10,000 to 1150. 13,80,000, sir. Output heat
Very
energy.
good. 13 lakh 18,000 is output. Now they
Output
have
heat energy.
mentioned you efficiency we have to find out, no? Thermal efficiency we have to find out.
Then input we have to calculate, sir. Input. Input energy is equal to mass into NCV. This is equal to mass into 700 liters.
Input energy is equal to mass into calorific value, obviously.
Calorific value. Mass is 700 liters, sir.
That you have to convert it into kg.
Kgs. So 0.95 they are given.
Right.
So liters by 0.95, sir. Then 0.9.
I'm sure it should be 0.95.
By
Divided by 0.95.
latest is TC is 9.0. $71 lakhs 10,526 input energy.
So what is your efficiency?
19.40.
19.4%.
Oh, yes, sir.
But actually, specific gravity given to us is 0.95,
Yes,
isn't
sir.
it?
Yes, sir.
So liter, if you have to convert to kg, 700 has to be multiplied by 0.95 or divided by 0.95. If you multiply, the answer is 21.5%.
Acha, acha. Liters to kg. I think we have to
For this, I will just give you one clue that in case of our domestic oil, it is 0.95 liter, which is equal to 1 kg. So if liter has to be converted to kg, isn't it? Then you
It
have
should
to
be
divide.
multiplied. It should be multiplied, sir. Sorry. Actually, 1 liter of water is equal to 1 kg.
It is for water because there both the things are same. 1 liter
Remaining
equal to 1
will
kg.
be only, everything will be less only, sir. Specific gravity of other fluids will be less than
Liter
the
will be
water.
liter will be less, kg will be more, right?
I did a mistake.
So ultimately, my answer is wrong, probably, right?
No, sir. If multiplication is correct.
Sir, your answer is correct, sir. 21.5.
Yes.
This is
If
correct.
liter has to be converted to kg, kg should be more, na?
Kg will be less, sir, always.
Sir,
Kg will be
what they
less.
have, what they have asked?
Thermal efficiency.
Ah, sir, 21% correct.
No, no, the 21% we feel that it is correct, but I'm still doubtful that 700 liter is equal to dash dash kg. We can ask to Google just now. Just wait.
No, no, 700 will be less only, sir, in kg.
700 liter equal to how much kg?
Hmm.
Yes, sir.
It is the furnace oil, na? 700 multiplied by specific heat they have given, 0.95, already given. Example.
1 liter equal to dash dash kg.
Equal to dash dash kg, which, sir, oil or
With
oil you
furnace
have?
oil. With furnace oil.
Furnace oil, na?
Hmm.
So,
We can check in Google, I am sure. Liter to kg
41725.
for furnace oil.
Because 665 kg, sir.
665.
Kgs. 700 into 0.95.
Right, right, right. So my answer is correct. Because 700 into 0.95 is 665 in the denominator.
That will because 641750, 54 lakhs.
So it is
it's
now
a,
clear.
it's a, yes, sir, it is.
Okay. So with all this, we will finish for today. This is the way we have covered 4 topics of paper 4, and in first four topics, if you have any doubt as on date, you can always call me. You can always be in touch with me. I have full, rather confidence that you will be able to go through all these 4 topics very easily. And if you have any problem, you are most welcome. Okay, so
Okay.
we'll finish for today.
Okay, sir. Yes, sir. Thank you, sir.
MCQs are there, no, sir. MCQs will just
Yeah, we can very well take MCQs. Oh,
MCQ.
sorry. Okay, okay. But again, wait for 1 minute.
Yes.
Whether the book is open on my desktop? Yes. I will have to rather. Okay.
We'll read out, sir, otherwise.
Yes.
Like misunderstood systems.
Page number 143, sir.
अरे बाप रे, how come? You all have got it in front of you, so I will not rather share the
Sir,
PPT
what?
now.
Sir, 143, page number
Yeah,
143.
I have reached. I have reached now.
Yes, yes. 143. Just
You are
close.
able to see on your on PPT screen.
Yes,
Yes,
sir.
sir,
Yes.
yes. We are seeing it.
Okay. Yes. Emissivity of ceramic coatings used in furnace. Is it right?
Yes, sir.
Yes.
You are all able to see and everything. Okay.
So we can be quoting
Emissivity of ceramic coatings used in furnace. Uh,
decrease.
Actually, this is topic 4 or
Same thing, sir. Same thing. Four only, sir.
right, correct. Emissivity of ceramic coatings used in furnace uh, decreases with increase in temperature or increases with increase in temperature. Uh, Ceramic coatings are particularly preferred for high temperature application in furnaces. So ultimately, emissivity
Increase, no, sir. To
increases with increase in
increase with
temperature is
increase.
correct. B is correct. Next is in reheating furnace scale loss will be scale loss will rather decrease with excess air should be minimum. We'll have no relation with excess air rather. See, this C is very, very correct because X% excess air has nothing to do with scale loss. Why? Because the scale always contains the materials like magnesium, silicon, and all that. And there does not contain any of these scaling contaminants. Air has got only carbon, nitrogen, hydrogen, and all that, which does not form scale at all. So it has no correlation with excess air. For optimum fuel consumption, the pressure at which furnace operates shall be slightly positive. Okay,
Correct,
slightly
sir.
positive. Then
Yes.
higher excess air in oil fire furnace will result in uh,
I
Reduce flame temperature.
reduced flame temperature. Right, it will affect on flame temperature. Next is heat loss through the opening in furnaces is directly proportional to radiation loss. Oh, because of opening in furnace, the radiant heat goes out, and that is why it is fourth power of furnace temperature. Because if in heat transfer, Q is equal to sigma A T raised to 4. So it is the fourth power of furnace temperature. So the heat loss is directly proportional to fourth power of furnace temperature. That is why heat loss through the openings is a very, very serious reason of deficiency in furnaces. Okay.
Fourth
Next.
power of absolute temperature, no, sir? Fourth power of absolute temperature or
Absolute, absolute. Including that 273 plus. Correct. Next is pick the wrong statement. Thermal efficiency of furnace increases by reducing the surface heat loss or minimizing the CO loss and unburnt loss is also correct, is most correct. Okay. CO
no,
loss
wrong
will
statement.
obviously, yes.
You have to pick
Wrong,
wrong
wrong
sentence.
statement.
Wrong
You
You
have
have
to
to
sentence.
pick
pick
up the
wrong
wrong. I'm
statement.
sorry. Uh,
Increasing the
Increasing
excess.
the excess airflow rate. Very correct. Very correct. B is correct. B is wrong. Oh, sorry. Again, I have to find out. Huh. If there is opening in the furnace body, heat in the furnace escapes to the outside mainly as radiation heat.
Right.
Because the heat inside the furnace goes out as radiant heat because the heat transfer is through the electromagnetic waves. Okay. Furnace wall heat loss does not depend on stock to be heated. Okay.
Yes, sir. Stop to me.
Furnace wall heat loss.
Which property of ceramic coating influences the energy saving in furnaces? Emissivity.
Emissive,
Right.
emissivity.
Right. And this efficiency is already solved by us. This problem you only have solved.
Right, sir.
What was our answer? 59%, that is 60. 59.9 was our answer. Do you remember?
Yes, sir.
Yes, sir. Yes,
So A is the correct answer. Okay. So
yes,
with
sir.
this we will finish for today. Thank you.
Thank you, sir. Thank you.
Yes, I was told that Mr. Borgaonkar sir will join. I will check and I will let you know. Okay, wait. माझं झालं पण बोरगावकर सर आले नाही.